Hi there. So we're looking at a situation where there are two lines in 3D space, two skew lines, a red line and a black line. This basically means that their lines do not meet and they're non-parallel. So we're going to try and find the shortest distance between those two lines. So we need to find a vector that's perpendicular to both the red and the black line, and then find the distance, or rather the magnitude of that vector. So we're going to create a vector RS, which is perpendicular to both the black and the red line. And then we're going to overlay two planes which contain both the red and the black line independently. And the dashed line, which passes through S, is actually parallel to the black line that passes through R. Now we're going to introduce 2 points, P and Q, on the two lines, arbitrary points, it doesn't matter where they are, and this is going to create a vector PQ. So you can see we've got a point on the black line P and a point on the red line Q, and a vector that goes between the two of them. And from this we're going to generate a triangle. The triangle is actually going to be made up by touching the dashed line, and from P up to the dashed line, and then from the dashed line to Q. So we have the vector Pn, and we have the vector PQ, and the angle between them, which is theta degrees. And you can see that the two vectors Pn and the vector Rs are both parallel. Okay, so that basically means that the modulus of the vector Pn, i.e. the size of the vector Pn, or the magnitude, so we're writing this down here, magnitude of Pn is actually equal to the magnitude of Rs. And sorry, I'll write Rs, not SR, I'll be consistent. And that is the distance that we're looking for, the shortest distance between the two skew lines. So we're going to shrink the diagram down now and do some annotation, and we're going to work on some robust method which is going to enable us to work out the distance Rs that we're looking for. Okay, so I'm going to label a few things now. I'm going to label our vector NP. Okay, and here's our angle theta, which is the angle between our vector PQ and vector NP. And remember, NP is actually parallel to RS. Okay, so if we can find the modulus of NP, therefore we can find the modulus of RS, which is our distance. So I'm going to put this up, down here. I'm going to say the modulus of RS is actually what we're after, which is equal to the modulus of NP, which is something we can calculate, which is actually equal to D, and D is our distance we're looking for. Okay, so you can see from our triangle PNQ that this is going to be 90 degrees up here, so I can state that the modulus of NP, which is something we would like to find out, is actually equal to the modulus of PQ times cos of the angle between them, cos theta. Let's just rewrite that, it was a bit messy. Okay, so since we know the points PQ, because there are 2 points we can pick on those two lines L1 and L2, the red and the black line respectively, we can work out the mod of PQ, and therefore we can work out the mod of NP from that, and therefore we can work out this mystery distance, the shortest distance between the two skew lines, which is what we want. Now, you'll notice that NP and RS are both perpendicular to those planes, and those planes have both got a normal vector, which I'm going to call n, which is at 90 degrees to the plane. I'm going to use the top one. So you'll probably notice that mod PQ cos theta looks something like it belongs in the dot product. So I'm going to actually write this relationship down. N, which is our unknown vector, which is the normal to one of the both planes. Okay, if I dot that with PQ, okay, I will get from the dot product relation mod n mod pq cos theta. So you can see that we have the mod pq cos theta up here and here. So all we have to do now is just divide both sides through by the mod of n, the normal vector. Okay, so I end up with n dotted with pq divided through by the modulus of n, and that's going to give us our value pq or mod of cos theta, which is in fact equal to our distance d, which is what we're looking for. So we now have a very robust relationship between our normal to the planes, our vector PQ, the vector between two arbitrary points P and Q on the lines, and the size of our normal vector to the planes. And we will be able to therefore work out quite quickly that shortest distance, which I will go through as an example. So, as you can see, we've now given the lines some vector equations. The orientation of the vector lines is just completely arbitrary. So, the first thing I'm going to do is figure out what the vector PQ should be. So I said we can choose arbitrarily any point on line L1 or line L2, the red and the black line. But what would be logical is, first of all, we could set lambda equals 0 in our first line, and that will get a position Q. Sorry, L1 is the black one, so in fact it'll be P, and that will give us a position vector 2, 1, negative 2, setting lambda equal to 0. And then Q, we can do exactly the same thing, so we can basically set mu is equal to 0, and that will give us our position of Q to be 350. From that, we can work out PQ, as you should know from your basic vector definitions. That would be Q subtract P, so therefore our vector PQ will be equal to 3 minus 2, which is 1, 5 minus 1, which is 4, and 0 subtract negative 2, which is going to be equal to positive 2. Okay, so there's our vector PQ. So we're part of the way where we want to be. The next thing we need to do is figure out what the normal vector n is. Now, I'm going to set n to be a, b, c, three unknown parameters a, b, and c. So we are needing to determine that. But what we do know is the vector n is actually perpendicular to both L1, the direction of L1, and the direction of L2. So if we dot a, b, c with, first of all, our L1 direction vector, which is going to be equal to 205, we know that that's equal to 0. So from that, we can say that 2a plus 5c equals 0. And we can create a relationship between a and c. So 2a is equal to negative 5c. Okay, so I'm going to call that equation 1. And I'm now going to dot our ABC, our normal vector, with our direction vector for L2, which is negative 5, 3, 4. And because it's also perpendicular, we know that dot product is 0. So that negative 5a plus 3b plus 4c equals 0. So we're going to call that equation 2. Now, if we look at equation 1, the parameters a, b, and c of our normal vector are actually just ratios, and we can choose any value of a and scale up b and c accordingly. So to make sure that they're integers, just for ease, we can say that a is equal to 5, because I know that that will give us 10 equals negative 5c. And because obviously 5 is a factor of 10, we get c is equal to negative 2. So we've already got two parts of our normal vector, a and c, and we can fill those in shortly, but I want to try and now use my second equation on the right hand side to work out what our value of b is our missing missing parameter. So a is equal to 5, b is equal to, what we're after, and c is equal to -2. Okay, so if we plug everything into our equation that we know, we've got -25 plus 3b minus 8 equals 0, and that simplifies to 3b is equal to 33, so b is equal to 11. Okay, so we can plug those things in, and we can now get our normal vector, which I'm going to put up here. Our values of a, b, and c are equal to 5, 11, and -2. So that's our second piece of the puzzle, and we can now plug things into our relationship to work out our value of d, the distance between the two skew lines. Okay, so here we are with our vector PQ and our normal vector to the two planes. And if you remember, the distance, or the shortest distance between the two skew lines, d, is equal to n dotted with PQ over the modulus of n. Now, this relationship you can quote directly in an exam. You don't need to prove it, but it's a very, very straightforward method of finding that distance we're after. So let's first of all dot n with PQ. So that's going to be equal to 5, 11, -2, dotted with 1, 4, 2, and that will give us 5 times 1 plus, whoops, I should have got equals, same over here. 5 times 1 is 5, plus 11 times 4 is 44, plus -2 times 2, which is subtract 4, so our dot product is actually equal to 45. And now we need to do is determine the modulus of our normal vector. So just using 3D Pythag, 5 squared plus 11 squared plus -2 squared, or just 2 squared. And that gives us root 150. Now we can simplify that because I know that that's equivalent to root 25 root 6, because 6 lots of 25 is 150, so that becomes 5 root 6. So if we plug in what we now know, so our dot product, n dot PQ was equal to 45, and our mod n was 5 root 6. Okay, we can simplify that, divide top and bottom by 5, and we get 9 over root 6, multiply through by root 6, and we get 9 root 6 over 6, and that further simplifies nicely to 3 root 6 over 2. So there's our shortest distance between those two skew lines. Thank you very much. We're done.
Okay, so you can see a rather complex looking diagram at the moment. The XY plane, you can see here's the X axis and the Y axis, and the Z axis vertically out. Then if I rotate this, you'll see the black line and the red line as we've just been working on. You can see that the two lines are within those two planes, and we can see our vector PQ, and we've also got another vector which is perpendicular to both, PR, which is our shortest distance, which according to this is 3.67 units. And if you simplify, that's a much better view. If you simplify the surd, which we just calculated, in fact it goes down to 3.67 units. So we have nailed that one. Okay, thank you very much.